Welcome back, everybody. I am absolutely thrilled to have you here for another explainer. Today, we're putting together the ultimate masterclass study guide on a real cornerstone of organic qualitative analysis. We're talking about the carbonyl reaction. Now, whether you're gearing up for a competitive chemistry exam or, just trying to wrap your head around intermediate molecular mechanisms, this explainer is designed to map out exactly what you need to know, step by microscopic step.
Okay, let's dive right into this. Imagine you're standing at your bench in the lab, and you're handed a test tube containing a completely unknown substrate. Your task? Figure out if there's a primary amine inside. Now, you could run a battery of complex instrumental analyses, or, you could just follow your nose. The Carbylamine reaction is famous, or maybe infamous is the better word, because its macroscopic reality is incredibly visceral. If a primary amine is present, this reaction is going to produce an overwhelmingly foul-smelling odor. It's a qualitative sniff test that chemists have literally relied on for generations.
To get you completely exam ready, here's our roadmap for today. 1. The primary amine sniff test. 2. Creating dichlorocarbene intermediates. 3. The nucleophilic attack phase. 4. Why secondary amines fail. And finally, 5. Cyclopropane synthesis contrast.
All right, starting with Section 1, the primary amine sniff test, a rather pungent qualitative test.
What's really interesting here is the sheer precision of the vocabulary. I highly recommend screenshotting these formal names as a study aid for your notes. The carbylamine reaction is also formally known as the Hofmann isocyanide synthesis, named after the chemist who discovered it. At its core, it's a chemical transformation that converts aliphatic or aromatic primary amines into isocyanides, which, by the way, are also called carbylamines. To make this whole thing happen, we need two absolutely crucial reagents, chloroform and a strong base, like potassium hydroxide. And the result? That distinctive, terrible odor of the isocyanide product that acts as our main indicator.
Before we shrink down and tackle the mechanism, you really must lock down the balanced chemical equation. We start with one molecule of our primary amine plus one molecule of chloroform. But pay super close attention to the stoichiometry right here. We need exactly 3 molecules of our strong base, potassium hydroxide. You heat this mixture up and it yields 1 molecule of our foul-smelling isocyanide, alongside 3 molecules of potassium chloride and 3 molecules of water. Memorize that exact 1:1:3 ratio for the reagents for sure. It will definitely save you on those tricky multiple-choice questions.
Moving right along to Section 2, creating dichlorocarbene intermediates. This is the alpha elimination phase.
To truly grasp the carbylamine reaction, you absolutely have to understand alpha elimination. This is a massive favorite for examiners to test. Alpha elimination is a reaction pathway where a carbanion is actually formed in the very first step. That carbanion then subsequently loses a leaving group, which in this case is a chloride ion, to form a highly reactive intermediate. So let's take a look at exactly how this plays out with our specific reagents.
So here's the dynamic sequence of the alpha elimination. Step 1. The strong base, or hydroxide ion, aggressively abstracts an acidic proton right from the chloroform molecule. Step 2. This dehydrohalogenation actually births a trichloromethyl carbanion intermediate. And then, Step 3. This carbanion rapidly eliminates a chloride ion. What gets left behind is the real star of our show, dichlorocarbene. This dichlorocarbene intermediate is highly reactive and very electrophilic, meaning it is just desperately hungry for electrons.
Okay, let's move to Section 3 and see how this all builds. The nucleophilic attack phase, forging the isocyanide.
So our electrophilic dichlorocarbon is kind of prowling around the solution, and boom, it finds our primary amine. Now, the primary amine has a nucleophilic nitrogen atom with an unshared lone pair of electrons. In Step 1, that nitrogen lone pair directly attacks the empty orbital of the dichlorocarbon. Once they're locked together, Step 2 kicks in. We start seeing successive base-mediated deprotonations. Basically, the strong base strips away the remaining hydrogen atoms from the nitrogen. Finally, in Step 3, the stripping action causes the elimination of the 2 remaining chloride ions as hydrochloric acid, which ultimately forges a really powerful carbon-nitrogen triple bond. And it's that exact triple bond that is the defining structural feature of our final isonitrile or isocyanide product.
And this brilliantly illustrates exactly why this topic is just so crucial. When you look at competitive exams, like this snippet from a WBJE chemistry sample paper, for instance, they rigorously test your understanding of these mechanistic pathways. Whether it's the redox disproportionation in a Canizar reaction, aldol condensations, or this alpha elimination-driven sequence of the Hoffman Carbylamine test, examiners don't just want you to know the end products, right? They want you to prove that you understand the exact microscopic movement of electrons, protons, and intermediates.
Which brings us to Section 4, Why Secondary Amines Fail, the big exception to the rule.
Here is a massive pro tip that you just absolutely must commit to memory. The carbonyl reaction is entirely specific to primary amines. Whether they're aliphatic or aromatic, like aniline, they give a positive test, forming that stable, foul-smelling isocyanide. But secondary and tertiary amines, they will always give a negative test. And why is that? It's simply because they physically lack the required hydrogen atoms, or protons, on the nitrogen atom. Remember those successive base-mediated deprotonations we just talked about? Well, a secondary amine only has one proton to give, and a tertiary amine has absolutely zero. Without those protons to strip away, the whole reaction basically hits a brick wall, forming unstable products instead of our target isocyanide.
And finally, Section 5, Cyclopropane Synthesis Contrasts, Alternative Carbene Pathways.
So the crucial point here is understanding the sheer versatility of the dichlorocarbene intermediate. In the carbamyl reaction we've been studying today, we pair dichlorocarbene with a primary amine to yield an isocyanide. But what if we change the partner? In cycloalkane chemistry, if we take that exact same dichlorocarbene, again generated from chloroform and a base, and introduce it to an alkene instead of an amine, the carbene adds directly across the double bond. And the result? A substituted cyclopropane ring. It's the exact same highly reactive intermediate, but a completely different synthetic application.
Which brings us to a really fascinating thought to leave you with today. We've seen how forcing an alpha elimination on simple chloroform unleashes a molecular tool powerful enough to act as a chemical sensor for amines, or even a structural builder for cycloalkanes. If we can manipulate these highly reactive fleeting carbenes to do our bidding like this, what other microscopic building blocks are just waiting to be synthesized in the lab? Keep that curiosity alive as you study, really focus on the mechanisms, and you'll absolutely ace this topic. Thanks so much for learning with me today on this explainer, and I will see you in the next